Hello students, in this session let us study about the methods that are available for determination of the spot speed value and how the data collected has been represented. So we have already listed out the methods that are involved. The one first method is the one which require the direct measurement of time, and if you know the value of the distance, so we can determine speed as the distance divided by time taken to move from in that particular distance. So using that relationship, we can determine what is the spot speed value. The second methods are the one which doesn't require the determination of time. So one example is the radar speedometer, and the third method is the photogrammetric methods. Okay, so within the first method, the first one of the method, the most commonly used method for determination of the spot speed study is by using the inoscope. Okay, so what is an inoscope? Inoscope is a device which is as shown in the figure. Okay, so it consisting of L-shaped box. Into that L-shaped box, a mirror will be attached to it, and the mirror will be attached to it in such a way that it is at an angle of 45 degree. So the angle suspended here is the 45 degree. And what is the purpose of forwarding the inoscope? So now in the direct timing procedure, what is the drawback we had? It was involving the reaction time of the two drivers. So now to overcome the drawback, okay, so we are reducing the number of observers that is required for the collection of the data. And also when the direct timing procedure is adopted, okay, the judgment of passage of vehicle at those two reference point, so there used to be an error because we sometimes wrongly judge even the vehicle does not pass the reference point at all, but we may assume that it has passed the reference point, we will stop the clock. Okay, so that such types of error, what it is there, that we call it as the parallel axe error. Okay, parallel axe error. So that is the one of the drawback using the direct timing procedure. So this parallax error can be eliminated with the help of inoscope. You can accurately judge whether the vehicle has passed the reference point or not. So that can be accurately seen with the help of inoscope. So now how does it function? So what is an inoscope? It is an L-shaped box which is open at the both the end, into which a mirror is set at an angle of 45 degree. Okay, so how does it work? So when the inoscope is bent, it will bend the line of sight of the observer in the perpendicular to the path of the vehicle. So now you can see here, this is the direction in which your vehicle will pass. Okay, so the moment in which the vehicle is passing, an observer will be stationed at the perpendicular direction. As soon as the vehicle passes the reference point, the observer can see the passage of vehicle in the mirror. Okay, so that the observer will be standing in the perpendicular direction. Okay, so angle between these two is the 90 degree. So the passage of vehicle can be seen by the observer. As soon as he see the vehicle in the mirror, he will switch on the stop clock. To that, how the how the timings can be recorded. So here this is the figure 1. In the figure 1, here we have the first reference point and the second reference point. At the first reference point, a inoscope will be placed. Okay, so this is a method when only one inoscope is used. So in the first reference point, a inoscope will be placed, and at the second reference point, our observer will station himself at the second reference point. So now how the observations will be taken? So now when the vehicle passes the first reference point, the observer who is standing at the second reference point can see the image of the vehicle in the mirror. Okay, so as soon as he see the passage of vehicle in the mirror, he will start the stop clock. Okay, that let it be the T1, and once the vehicle passes in front of him at the second point, he will note down the time, stop the clockwork. So that will records the what is the time required for the vehicle to pass between the point between the two reference point. So you will be knowing the distance between those two reference point, nothing but the base length. So the distance divided by time taken by the vehicle to pass two reference point. Using that you can determine the what is the spot speed of the vehicle. So second thing is we can also have another variation, that is you can use the two inoscope can be used. So when the two inoscope is used, an observer station himself at the middle of the 2 points and the inoscopes will be placed at the two reference points. At the passage of two vehicles at these two reference point, he can see that, and when the vehicle passes the first reference point, he'll start the stop clock, and similarly when he vehicle passes the stop clock, he'll second reference point, he'll stop the clockwork. Okay, and with that you'll be knowing the what is the known distance between two reference point, distance divided by what the timings recorded in the stop clock. So that that will gives you the what is the value of spot speed. Okay, so by using the inoscope method you can eliminate the disadvantages what we had in the direct timing procedure, that is the parallax error can be eliminated. That's the main advantage. Next method is the radar speedometer method. Okay, so I think you might have seen this radar speedometer. It is one of the successful tool in the hands of traffic engineers, or sorry, the police, the traffic control police, to regulate the speed values. So you can see here in this picture we have the traffic interceptor. It is fitted with the radar speedometer. So if any vehicles, it will send the signals. Okay, it will record what is the speed of the vehicle in front of it. Okay, so if by any chance if the in the road the speed is, for any particular road the speed is 60 kmph, if in the radar speedometer if the speed value shows more than 60 kmph, immediately policeman will stop the vehicle and he can be subjected to the fines. Okay, and now here how it works and how we can measure the speed value with the help of the radar speedometer. So this radar speedometer works on the Doppler's principle. So what is that Doppler principle says? The speed of any moving vehicle body is proportional to the change in frequency between the radio wave transmitted to the moving body and the radio wave received back. So now, so for the radar speedometer, a radio waves will be sent to the vehicle. So that will have some frequency F1, and this radio frequency, once it hit the body of the vehicle, that will be transmitted back to the radar speedometer again. So the frequency of the radio wave transmitted back, that will be F2, and difference in frequency F1 as F1 minus F2. So this will be proportional to the speed of the vehicle. You will have a chart which will show the distance relationship between the speed and the frequency of the vehicle. So knowing the value of the frequency or difference in frequency value, you can determine what is the speed at which the vehicle is traveling. Okay, so but it has some you need to have some initial adjustment for an accurate data. So that includes a vehicle has to be, the instrument has to set up near the carriageway at the height of 1 meter. Okay, from the carriageway to the height of the speedometer should be 1 meter, and it should be kept in such a way that the angle of transmission of radio wave to the vehicle must be as small as possible, that is say within 20 degree. Okay, the speed of vehicles in the both the direction of the road can be determined with the help of the radar speedometer. So this is like most commonly used in the speed regulations. The next method is the photogrammetric method. So now what the photogrammetric method, how it will be used. So here will be the time-lapse camera photographs can be used. So this time-lapse, with the help of time-lapse cameras, you will frequently take the photographs of the vehicles moving. So time-lapse camera means for every few seconds, photos will be taken. So those photos has to be projected on the screen as a film, and passage of any vehicle can be traced there in the film when it moves. So you have to, when the vehicle is moving, so you will be knowing what is the first reference points. Again, note down what is the time required for the vehicle to pass two reference point in the video. In the video you will run it as a film. In the film, in this on the screen, just note down the time passage of the two vehicles. So once again, the distance divided by the time will gives you the speed of the vehicle. So this is the how the record data can be recorded with the help of the log sheets. So when we have already seen how it is used in the vehicle volume survey, similar to that, we need to give the details about the observer, timings, place where it has been recorded, what is the weather condition, and here the vehicles numbers, because we need to know for which vehicle you are noting out the speed values, or registration number has to be written here, and what is the speed value. So like this we need to write it for all the vehicles. For example, you have consider 100 vehicles. So for all the 100 vehicles, what is the registration number and what's the speed value has to be written here in the data collection form. So now once the data is ready, next is the representation, how the value has to be here. You will have the speed of various vehicle. So now we have to count how many number of vehicles you are having which is traveling at the speed of 20 to 10 to 20 kmph. That you need to count. And how many vehicles are in between speed 20 to 30 kmph, how many are there between 30 to 40. So like that, 60 to 70, 70 to 80, and so on. So like that, out of 100 vehicles what you have, the data has been collected. Within that, how many 100 vehicles, how many are in the following groups: 10 to 20 kmph, 20 to 30 kmph, right? That vehicles has to be first, grouping the vehicles into the speed range that you. So now here, spot speed steady representation. The first thing is you have to group all the data what you have collected into the particular speed groups. So how do you say the speed group? For example, in many you take the NH value, NH, okay. So your speed value will be 80 to 100 kmph. At max, your vehicles can travel at 100 kmph. So now what you have to do is, in between, the maximum speed is 100 kmph. So the minimum speed can be this 0 kmph. So now within 0 to 100 kmph, you have to group into the various data. For example, the speed range between 10 to kmph, 10 to 20 kmph, 20 to 30 kmph, 30 to 40 kmph, like that you have to group into the various speed range. No, so once you've noted out, that has to be plotted into the graph. Okay, so how do you plot the graph? So when you average speed of the vehicle, so that is the distributing that call it as the frequency distribution table. The data was you collected, first you will put it into this frequency distribution table. What is the frequency distribution table? We will have the speed range. So like that, 10 to 20, 20 to 20, 30, like that the speed range will be there. And also we will have the number of vehicles within the particular speed range will be there. So that the table we call it as the frequency distribution table. So after this we will plot. Once the frequency distribution table is ready, we do have certain calculation, and I'll show it to you when we do the calculation. Once that is frequency distribution table is completed, the data what you have it as the frequency distribution table, that would be transferred into the graph. That we call it as the frequency distribution graph. How do you plot the graph? In the graph, you need to take speed value on the x-axis. The speed should be in terms of kilometers per hour, and the percentage frequency in the x-axis. So and plot the graph, what the values you have it in the frequency distribution graph, that has to be plotted, and which will yield the normal distribution curve. It's a bell-shaped curve, we call it as the normal distribution curve. So what the curve we got it as, that curve we call it as the frequency distribution curve. Okay, the peak value in this, that we call it as the modal speed. So modal speed is nothing but the mid speed in which, or average speed, all the vehicles are expected to travel. Or you can also use the bar graphs for the representation of the speed, but most commonly we will use the normal distribution curve. Okay, so once it is ready, the next is we will read out. Okay, cumulative frequency distribution graph. So in the cumulative frequency graph, we will take speed on the x-axis and cumulative percentage frequency on the y-axis. Okay, so when you plot the graph, once again you will yield an S-shaped curve here. Okay, so once you got this curve, so here plot for the 50, note down what is a 15 percentage, note down 85 percentage, note down what is 98 percentage. Okay, so at these percentage, draw one horizontal line, draw the horizontal line, and then drop it down. Okay, so what speed value you will get, that speed we will call it as the 15 percentage speed. So what does it indicate, 15 percentage speed? It says that, so for example, I've got the speed here as 30 kmph. Okay, so out of all the vehicles, 15 percentage of vehicles are traveling at the speed below 30 kmph. Okay, and you take 85 percentage kmph. So at the 85 percentage, you plot a line. Okay, drop it down. So you got the value around 62 kmph. What does it say? The almost out of all the vehicle, 85 percentage vehicles are traveling at the speed of 62 kmph and below it. Okay, and remaining are exceeding the speed. Okay, so that remaining 15 percentage of vehicles are more than the 62 kmph speed. And why it is required, plotting all this percentage, why it is required? So usually when we, this will be the, these percentage will be used for the speed regulation and the design. Okay, 15 percentage speed is taken as the lower speed limit. So in usually in the road stretch, you will have the upper speed limit and the lower speed limit. Okay, so 15 percentage speed is the lower speed limit. In that, it means to say that in that road, the speed value, the speed of the vehicle should not go below this 15 percentile speed. Similarly, 85 percentage speed is the safe speed or maximum speed that can be allowed here. If any vehicles are traveling at the speed more than 85 percentage speed, let's say that they are on the overspeeding. Okay, similarly, the 98 percentage speed, that is used for the design of geometric aspect. So how in the traffic volume you will take 30th hourly volume as the design hourly volume. Similarly, in the spot speed value, 98 percentile speed will be taken as the design speed. And we have one more, that is the 15th percentile speed, that we call it as the median speed. So median speed is nothing but the what is then average speed at all the vehicles are traveling. So in the normal distribution curve, you will get the peak point. So this is nothing but the median speed. So that is, we can get it from the cumulative distribution graph using the 50th percentile speed. So that means today that 50 percentage of vehicles are traveling at speed below the what value you get at the 50th percentile speed. Okay, so this is how data what we have collected in the spot speed studies can be represented.